Welcome to this screencast on hash tables. This is our last abstract data type that we'll be talking about this semester in ICS 211. So what are some of the goals for having a hash table? We've had other abstract data types. One of the key goals to abstract or a hash table is that we want to access the item based upon its key. The key is some aspect of the item. It may be a particular piece of the item or some label or something on the item, and we want to access it based upon this key. We don't want to have to search through the entire data structure to find this key. We want the access time to be constant, or on average big O of 1. So we want it to be quick. So we want to be able to somehow calculate some index into the table based upon this key. So how do we do that? We transform the key into first we create a hash code from the key. So we use some calculation that takes this key and creates an integer based upon this key. We then mod that integer by the size of the table. That gives us the index of the item, where we want to put the item in the table or where it should be in the table. And then if we have that index, we then have to resolve any collisions where we want to stick the item into slot 2 or index 2, but there's something already there. We need to resolve that collision, so we don't want to overwrite the thing that's there, so we need to find another place in the table to store this particular item. So there's a couple of ways to solve this collision problem. So how do we, well, one of the problems is that there are more hash codes than the size of the table. We don't have infinite size table. For example, if we had a table of size 200 and we're using the Unicode as our hash, then we'll see where the right parentheses Unicode is 41, the small letter n with a tilde is 241. When we mod them by 200, they both have the same index of 41, and that's called a collision. We will want to store the right parentheses and the n with a tilde in the same index in our table. We want to put it in the same spot. We have to somehow resolve that issue. So that's collision. We want to be able to calculate hash codes. First off, we want to create hash codes. The goal is we want to distribute the hash code value over the range of integers, and we want to distribute it randomly, so we want it sort of evenly spaced. We don't, two strings like sign and sing should end up different spaces in the index or the integers. A simple right off the bat thing would say, well, why don't I just add up the values of each character for a string? But unfortunately, that simple algorithm doesn't work because addition is transitive. So when you add up sing and sign, they come to the same value. So those two different keys collide using that simple algorithm to generate our hash, so that's not a good idea. So we're going to look at a different one, and the Java string hash code uses an interesting way of producing hash codes by taking each individual character, multiplying it by 31 raised to that string's position minus 1. So sing is s times 31 to the third plus I times 31 to the squared plus n times 31 plus g, whereas sign is s times 31 to the third plus I times 31 squared plus g times 31 plus n. Those two integer values will be different and will not collide. And so using prime numbers generate relatively few collisions because of the way that primes multiply and divide. I'm going to give you a quick example of the Eclipse hash code method. So if I go to source, generate hash code in equals, I get to choose. So I'm going to choose my two endpoints in my segment class, and we'll note right here, just show what Eclipse is doing for us. Selects a prime number, in this case 31. It creates a result, and the result is prime times result plus either if the endpoint is null, it shows a 0, or it uses the hash code. So, and then result is prime times result. So that's where we get the 31 squared. So we get the positioning, and then we return the result. So the Eclipse hash code by default function that they give you when you generate it, it uses the same idea of a prime number raised to a power, time, or adding the individual value of the component that you're using. So that gives you a unique hash code that is randomly or reasonably randomly distributed across the integer space. Just wanted to give you that example. So Eclipse uses the same kind of algorithm for generating their hash codes. Another thing about hash codes is that string hash code cannot be unique because there are more strings than there are integers in the Java integer range. So string hash code will return the same hash code for different strings. That's just, it will, but the string hash code function or method does a good job of distributing the values evenly throughout the range. So the probability of two strings having the same hash code is very low, but it is not 0. And the probability of a collision when you're talking about using that method hash code and modding by the table length is proportional to how full the table is. So the more entries you have in your table means the more chance that when you calculate the index you'll have something there. So we got to resolve that. So but generally we want to have a larger table, but we want to really remember this, how full the table is, because if we have a huge table with one item in it, we're wasting a lot of space. So we want to keep the table fullness to be low or not. We don't want to get too high because we have collisions. So what is a good hash function? It should be fairly simple and it should be efficient to implement. We don't want to use a big O of n hash function to avoid doing a big O of n search, because if you could just find the item, you can just start at 0 and go through it until you find it. That's a big O of n, so why spend a big O of n operation to find its index when you can just loop through all the indexes? So we want to have a reasonably quick hash function, and that math that we showed for doing the prime times is a reasonably good hash function. It's quick, it's basically big O of 1, it's not that expensive. So how do we deal with the collisions that we know we are going to get when we have a full or reasonably full hash table? There are two different ways. One is called open addressing and one is called chaining. The open addressing is an idea that each element in the table holds an item, and when we have a collision we use a probing method to move down the table or increment our index until we find an emptier place to put the item, and we'll talk about that next. So to access an item in the table, we calculate the index for the key. If the item there has the same key, then we found the item. If that item has a different key, then we have a collision and we increment the index by 1. This is linear probing, we move 1 down. And we check the item in the next slot. If we get to the end of the array, we just go back to 0, so we're going to use a circular array. So we're just mod by the table length to get the answer, the index. And if you find a null, that means the item is not in the table. If you get back to the original index that you calculated for the key and you haven't found it, the table is full and it's not there. So the algorithm is you compute the index, which is the hashcode mod table length. If the thing at that index is null, item's not in the table, we're done. Else, if it's equal to the item we're looking for, we found it. Else we continue incrementing until we found the item or a null, or that index is back again to the original index, which means you've gone and searched the entire table. You got to watch for that because you can get an infinite loop if you don't. If you get back to that original index, you don't want to keep going. So here's an example of linear probing with 5 strings: Tom, Dick, Harry, Sam, and Pete. Their hash code, we mod the hash code by the size of the table, which is 5, and then we're going to stick the strings in starting with Tom. So Tom goes into slot 4, and then we want to add Dick, but Dick's index is 4, so we need to increment 4, make it and then 5, mod it by 5, which makes it 0, and so we stick Dick into slot 0. Harry is got a index of 3, so we just slide him in. Sam has a 4, Tom's already there, increment mod 5, there's something there, so now we stick Sam in there, and then Pete, who has a 3, my slides off, we increment to 4, we go to 0, we go to 1, and then we stick it in. And so now we can talk about how we would retrieve. If we try to retrieve Tom, we look at Tom's index is 4, we find it immediately, big O of 1. Harry, the same thing. The other 3, if we look for Sam, we are going to go look at 4, it's not there, we go to 1, it's not there, we go to 0, it's not there, we go to 1, we find it. Same thing with Pete. So Dick, Sam, and Pete, we have to do a little bit of linear probing, but again, that's not terribly bad. It's close to big O of 1. It's not big O of n, except for in Pete's case where we had to go all the way around. So let's take a look at a larger table example. So now, again, because we have a different size table, the hash codes are different. And so Tom goes into 3, Dick goes into 5, Harry goes to 10, Sam goes to 5, there's a collision, and then Pete goes to 7. So we only had one collision in this case. So Tom, Dick, Pete, and Harry, their access is big O of 1. Sam, we have to do a collision resolution for Sam. The best way to reduce collision is to increase the size of your table. It is also a good idea to use a table that has a prime number for a size. So when we want to delete an item out of the hash table, we just can't delete the item by setting that item to null, because if that item is in a collision chain, we need to have not a space there. We need to have to mark that item as still being there but not there. It should be available. The space is available for insertion but previously occupied, so if we're doing a search, for example, Sam, the collision would still occur and we would continue incrementing our pointer, our index. So you can't insert that available space until you make sure that the item's not already in the table, because you don't want to add this item into the table twice. So that is one thing that you have to search all the way to you find null before you insert at that first dummy, which does cause, this is one of the issues with open addressing and probing. So deleting items is difficult because you got to stick in a dummy item that indicates that the space is available if you check the entire table. It is a tricky way of doing things. So expanding the table size, so if you get close to being full, we'll want to grow this table size. So it's good to choose a prime number for your table size, and fuller tables lead to more collisions. So when it is sufficiently full, and that's up to you as the implementer of the hash table, we want to create a larger table, and we don't copy the items over because it's got a larger size. It has a different hash algorithm, the mod by the size, so we reinsert or rehash the values into the new table. So we recalculate the hash code, mod it by the new table size, and insert the item into the table, doing our probing if we need to, and we don't need to insert deleted items. We ignore them because they're gone. So it's quite easy to expand the table size. We just have to reinsert all the items in the new table because they have a new index. A second way of doing the probing is to do quadratic probing. Basically, linear probing tends to create clusters of keys in the hash table. So because we increment by 1, we're gonna, if you run into something, you're gonna go to the next one, and eventually you find the next open spot. That causes a cluster of filled in values, which then causes you to continue to probe, and it can lead to chains, which causes it to be a little bit slow. So the quadratic programming could reduce the clusterings because we use a quadratic series to do our increment. So the probe number gets increased. The index is the start index plus the probe number times the probe number, so probe number squared, and then mod table length. So if the hash code is 5, we'll go to the next one will be 6 if there's a collision at 5. We'll go to 6, 9, 14, and 21. The problem with this is that this calculation is time consuming, this probing calculation, because we've got to do a multiply, an addition, and a mod, which is expensive. A more efficient way is we can create this value k and then just increment the index by k and just double k each time. And so the example, if the k starts as -1, the incremental values of k are 1, 3, 5. The index is, because we're adding the index plus k each time, we end up with 5 plus 1, or 5 plus 1 plus 3, which is 9. So you can see that by keeping the old value of the index plus k each time through the probing, we're basically getting an n squared, or a quadratic equation, and the proof is basically that n squared is equal to 1 plus 3 plus 5 plus 7 plus 9, blah, 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 2 to the n minus 1 is n squared. So we're creating the square by using the summing instead of multiplying. So it's a much more efficient method of calculating the next probe than having to do the multiply and the add. We just have to do 2 adds, and 2 adds is much easier to execute than a multiply. So one problem with quadratic probing, another problem other than you got this complicated math, is that you don't check all the items in the table. Because you are skipping some, you may not consider all values in the table, and therefore you may not be able to insert something even though the table isn't full. And you can get to infinite loops when you're searching for an empty slot. You got to be very careful that you know where you started and that you're not just hitting the same things again and again and again. If the table size is prime and the table is less than half full, there's no problem. You won't have this. You'll find an empty slot when you're using quadratic probing. The problem is now you've got the table is twice as large. It's only storing half as much. You're wasting memory by having your table being twice as large as it really needs to be. So that's not a good solution for quadratic probing, and that's one of the issues with quadratic probing, is basically you need to have your table size be twice as large as it sort of needs to be. The alternative to open addressing and probing is to use a linked list at each of the table things. So the table holds a linked list of the items. So each table element is the head of a linked list. Each item in the list has the same table index, so when you calculate your index based upon your hash code and modding by table size, you then just search the list to insert it. Often the list is called the bucket, and sometimes this is called bucket hashing. So in the case, our previous example, where we had Pete and Harry collide at 1 and Tom, Dick, and Sam all collide at 4, you would just have a linked list with the items. So the linked list's average length is the number of items divided by the number of entries in the table. So that's the size L. One advantage, when you're searching the linked list, you know that they have, all those items have the same index. They have basically the same hash code mod by the table size. You can store more items than in the table than you have entries in the table, because the linked list could be longer, so you can store more stuff. It's nice. Once you determine items not in a bucket, you can then add it to the linked list. So you just traverse the linked list. If it's not there, you add it. It's very easy. To remove an item, there's no issues with these dummy values and stuff. You just delete it from the linked list. It's quite simple. It does, it's a more complicated data structure in that now you've got a table and linked lists, but it's once you understand and have used linked lists a lot, it's very easy to implement and use. So the load factor is basically the number of filled cells divided by the table size. So that's telling us how full a hash table is. So as we were talking about, the more full a hash table is, the more chance for collision, and the performance of the hash table goes down because then we have to do probing or we have to search things. So the load factor has the greatest effect on hash table performance because we have more collisions. Lower the load factor, better the performance. Access is going to be closer to big O of 1. If there are no collisions, performance for search and retrieval is big O of 1. So that's fantastic. It's very quick to get the item out of a hash table if the load factor is low. So that's a good thing. Dr. Knuth came up with a formula for figuring out how many comparisons you need to do for, and this is not, they're not collisions, how many times you have to compare. And so for open addressing with linear probing, he came up with the formula 1/2 times 1 plus 1 over 1 minus the load factor. So, and then for chaining, it's very simple because you go to the right place and then you just have to search that linked list, and on average the length of the linked list is the load factor divided by 2. So half the time you'll get there. So it's a very simple number of comparisons for chaining. It's a slightly more complicated formula for open addressing. So it's a way of comparing a open address hash table versus a chaining is the number of comparisons. So let's look at that. So we can calculate the load factor. Here's in the left-hand column the number of probes if you're using linear open addressing with linear probing, or if you're using a chaining. And you can see as the load factor grows, the linear the open addressing with linear probing has a lot of comparisons, whereas the chaining does not grow nearly as quickly. So you're just searching those linked lists. So now you can compare that to doing a binary search or of a sorted array. If you had 128 items, you need 7 probes to do it, which is more expensive than a 90% full table, even using linear probing. So a hash table in general, as long as it's less than 90% full, is better than finding something in a sorted array. So it is still more efficient for retrieving and adding items into a hash table than in a sorted array or a binary search tree, which is basically a complicated sorted array. So let's talk about the performance of trying to find things in a hash table or a unsorted array or even a binary search tree. Hash table, big O of 1, because calculate the index, we get it. Worst case, we have to do the linear probing, and it's big O of n. Unsorted array, we search it, big O of n. Binary search tree, again, as we talk about, it's basically log n, so that's quick, but that's not nearly as quick as big O of 1. And in the worst case, it's still big O of n. So in all these data structures, worst case is big O of n. So the performance of hashing is superior to even binary search tree, particularly if the load factor is low, and not even too low, 75%. But you then still have to have more empty storage cells, which is an issue because your hash table is going to be larger than your binary search tree. Well, it will be larger than your sorted array. So let's talk about storage requirements. Sorted array, you have n references, one per thing in the list. So it's efficient in storing the data. It's expensive to add things because you got to resort. It's expensive to get things because you have to search, but it is efficient in storage requirements. Binary search tree, same thing. There's no empty spaces, but you need 3 references per item in the tree, you need a reference to the data, you need the left pointer and the right pointer. So that's 3n references. So that's expensive. Open addressing, let's say we got an empty space at 25%. Since each item in the table is like a sorted array, you have a reference to the item, but since we have 25% empty, we basically have 1.33, 1 1/3 references, because we have a third empty space. So we have 1.33 times n references in the open addressing example. In chaining, we can reduce the size of the table to m, but then we have the load factor of our linked list. So the linked list at a minimum has a pointer to the data and a pointer to the next. So that's the 2L, and the load factor is how many, basically how many items in the linked list on average there are. So it doesn't have any empty space, but we have this hit on having the linked list. So that is expensive. And m is the number of items in the table, the number of entries in the table. Not the number of items. It's the length of the table. So, for example, we can say we want to store 6,000 items. So if we use open addressing with 75% load, that means basically we need 80,000 entries, because we need to take make sure there's enough room in the table so that we're at 75% load. So we have to do 1.3, which is basically 20,000 empty slots. And at that level of load, it's an average of 2.5 probes to get there. So the chaining we need to have, as the formula we were talking about, we have 20,000 entries. I'll calculate that times 2 times L, which is we have that many references. Sorry. So we have that. Go back. Sorry, got out of line. So in order to have 2.5 probes for open chaining, we can calculate our load factor. So C was 1 plus load over 2, so 2.5 is load over 2. So then we can multiply by 2, so we got 5 times 5 equals 2 plus L, so we subtract 2 from both sides. 3 equals L, and that's a load factor. The load factor is the number of items we're storing divided by the table size. So we can come up with the table size. So we need 20,000 entries for our chaining table to have the same probe number. So it has the same performance as our open addressing. But so now we have a table size of 20,000. So now we need to calculate how many references we need. So it's 20,000 times 2 times the number of entries, right? Because we're going to have 60,000 things in our linked list, and each linked list node has 2 references. So 2 times 60,000. So we need 140,000 references, which is 175% bigger. So the amount of memory stored in our chaining hash table is 175% of our open addressing. So we're spending even more space. We're using much more space to store the hash table in the chaining model than we did in the open addressing, but that is still less than 3 times, right? So in a binary search tree, we need 3 references per item, so that would be 180,000. So the binary search tree is even larger than both of our hash tables. So the hash tables take less space than our binary search tree. That's it. Thank you for paying attention.